this lecture, we're going to actually finish our program of making sure we can do all the things with our new parametric equations that we could do with our kind of standard rectangular equations. So the last piece of the puzzle is a formula for the arc length of a parametric curve. And to find this formula, we're going to take the same approach here as we did to deriving the formula for the area under a parametric curve. We're going to start here with the formula for arc length that you've hopefully seen previously, right? This is how we would do this with a function y in terms of x. So let's see, we saw in a previous lecture that dy dx is dy dt divided by dx dt. So first I'll substitute that into the integral here. And let's see, now I'm going to substitute dx dt times dt for dx, right? And now we're integrating with respect to our parametric parameter t. So now we need to do a little algebra trick. I want to bring this dx dt inside the square root. Right, so what I'm going to do is I'm going to rewrite it as the square root of dx dt squared. Now I can combine the two square roots and distribute this dx dt squared to both terms inside the integral. This becomes the integral from a to b of the square root of dx dt squared times dy dt over dx dt squared times dx dt squared. And you see what happens now, right? This dx dt squared cancels with this dx dt squared, and that gives us our final formula. The integral of the square root of dx dt squared plus dy dt squared dt. All right, so let's see how we can use this. Right, we're going to do the same thing here as we did in our first discussion of the area under parametric curves. Work with something that we already know. In this case, we're again working with a circle whose radius is r. So to use our formula, we first need the individual derivatives. Dx d theta is r cosine theta, and dy d theta is minus r sine theta. So substituting those into our formula here gives us the integral square root of r cosine theta squared plus minus r sine theta squared all d theta. And we want a full circle, right? So we'll integrate from 0 all the way to 2 pi. Now, nothing in our formula ever becomes negative, right? Nothing no part of the integrand does. So we don't need to worry about the kind of canceling that we saw that we had to worry about in our original area example. So let's see, now we can simplify the integrand. This is still the integral 0 to 2 pi square root of r squared cosine squared theta plus r squared sine squared theta, square root of that whole thing, d theta. Right, so let's see, pulling out the constant r here, we would get the square root of r squared, which is just r. So this is r integral 0 to 2 pi square root of cosine squared plus sine squared. But that's nice. The square root of cosine squared plus sine squared is just 1. Of course, the square root of 1 is 1. So this becomes r times the integral from 0 to 2 pi of d theta, which is just theta from 0 to 2 pi. This is, so r times 2 pi minus 0, and this is just 2 pi r, which is exactly what we expected. That is the formula for the circumference of a circle. So that fills out our toolbox now for calculus methods with parametric equations. So in the next couple of lectures in the series, we're going to look at some specific examples, look at some kind of unusual cases, right? See how you can use this formula to actually do some calculations.